It should be exactly the same number of people as there are chairs. So we've got a couple of people missing. Are you down the side student? Okay. No. One of these screens isn't working, I'm afraid. We managed to move from the previous classroom. Some of you pointed out the previous classroom wasn't really fit for purpose. It's worth, pointing out this screen's not working as well. And if I were you, I'd complain about it. It's meant to work and it doesn't work. So when you complained last time, we got a better room. If you complain about the screen not working, then maybe next time we'll have both screens working as well. I think you're going to have to stay there. It's all right. Oh no. Okay. First of all, we need to go through the material that you've all been doing. So did you all actually get onto Blackboard and look through the material? So did you guys get on and look through?
We got there yesterday.
Oh right, that's not good. Everybody else though, did you actually spend some time and go through the stuff on Blackboard? Yeah, okay. Well, we'll quickly go through it for everyone that's not been through it or has been through it. You do need to go through it though, because there's quite a lot of stuff to come, so you need to try and keep up with it. This screen doesn't work either, so I'm looking at this one. So my eye's not great anyway, so just bear with me. Critically for you guys, and it's worth saying it for everybody else as well, remember, this is the assessment schedule, okay, because you always forget and always have to keep asking me. And for mine, the assessment is week 6, as you said before, so there's quite a lot of time before you need to do it. So ideally you should go through the stuff in Blackboard whilst we're during our first 3 weeks, but you've got time afterwards to do that as well, to spend on it. And also some of the stuff that's going to be on my test is going to be in the field trip, which is going in Neil Mitchell's weeks as well. So that's why my test is afterwards. So other things that we're going to be doing next week, which is the last week that you're with me, part of next week we'll be going through the stuff you're going to be doing on the field trip. So between now and then, what we've done so far is a bit of measuring. There's more of measuring, and there's all the predicting to do. And then there's also the preparation for the field trip. So there's quite a lot of stuff to fit in. There's plenty of time for you, as you know, because the contact time is only a small part of this, and you've got 300 hours of work time over the whole semester. So there's time to do this, right? Just because I'm not there beating you up over it. I don't need to say this, do you? Because you're all master students. But you do need to do this stuff. Okay, I was hoping you'd have worked your way through the first 3 of these things. If you remember, there was this little dialogue to do. Which I think you all did, because we were sat there and we were in class doing that. So you all did that. And then for you guys that weren't here, just to let you know, if you've not done this, what this is about, you can jump straight to the end if you like, because I know all of you have used the standard deviation before, and you've done basic statistics, and you could think, well, I don't really need to do this bit. So jump to the end. What we're doing here is defining the standard deviation, and ultimately, one of the tasks for you to do, again, it's not part of the assessment, but what the task for you to do is to write a short essay describing why standard deviation is the most commonly used measure of variability. And if you can understand that, then you're going to actually use the statistics correctly, the ones that rely on standard deviation. And the whole of this section really is taking you through deriving the standard deviation. Okay. Those people that have done this so far, they should be feeling like they're ready to write their short essay on why standard deviation is the most commonly used measure of variability.
It only said about it's on the slope of the normal distribution. Standard deviation is where the slope is linear. That's why we're using it. That's all it said about it. It works it all out and it's a reason for it on that slope.
As usual, I can't say that you're wrong. You're bang on, that's true. But the whole reasoning behind it, there's a whole lot there. You said a mouthful, really. Like a normal distribution, what's that got to do with anything? And that's what this is going through, really. Okay, well, what you're doing first of all was taking this large data set and deriving your own measure of variability. First of all, you're deciding why you need to measure variability. Okay, and that was the dialogue that's gone on before. That dialogue is deciding why you need to measure variability. And if you remember, there's two reasons why. I'm not going to say them again, but you do remember there's two reasons why. One of them is quite straightforward, and the other one's much more cerebral. Both of those could feature in the test. Okay, in the end of this, you've got a 1 hour short answer multiple choice test, and if that wasn't easy enough, I always kind of point out what some of the questions might be. Okay, so why do we need to measure variability? Why do we need to make multiple measurements? If the question was why do we need to make multiple measurements, you should all be all over it with your pair of answers. Okay, and then recognising that once we do need to quantify variability, then your task was to come up with your measure of variability, and working from first principles from your measures, what you might have as a measure of variability. You started out by thinking we look at the range, but you discarded the range because it only uses 2 of the data points, so that's no good. And then you move to this idea of measuring the mean and the difference between all the data points and the mean, and that all seems to make perfect sense. Okay, and there's a little problem with that. If you measure the difference between all the data points and the mean, and you add them together, you can see, well, if it's a big number, it means you've got a variable data set. If it's a small number, it's not very variable. But there's a little problem in that if you add up all the differences, the positive and negative differences, they all sum to 0. Okay, so you need to disregard the sign. Not difficult, let's just disregard the sign. So if you're doing it in Excel, you'd use the function ABS for absolute, which means it disregards the sign, and then you can add up all the differences between the means and all the data points. If you get a big number, it means you've got a variable data set. If you get a small number, it means you've got one that's not very variable. Another little hiccup, well, if we want to compare one data set to another, if the data sets are different sizes, if I've got a very big data set, I'm more likely to have a large number, but it doesn't mean it's more variable. So we need to normalise it against the size of the data set. Again, simple to do, we just divide by the number in the data set. And that's what we call a standard measure of variability. It's not quite the standard deviation, but for those of you that have worked out a standard deviation, you know it's really very, very close to the measure of standard deviation. Okay, and this was you going through that. There's some bits of Excel that you may not have used in doing this before, so it's worth doing this anyway. But that's the process that you're working through if you've done it or if you haven't. There's little videos to take you through that, doing frequency distributions, coming up with measures of variability, and ultimately deriving your measure of variability that's your own, really, and you should just feel like you've got some ownership of that. From a priori, from first principles, you work through. The starting point of this whole argument, if you remember, was to say we can't make a true measurement. That's where this starts. And really your argument about why standard deviation is the most commonly used measure of variability, really your argument needs to start with that. If you're going to write an essay about why something is the most commonly used something of something, well, why on earth do we need to measure variability to start with? And the starting point for that is because we can't make a true measurement. And again, something that I reinforced to everybody last week when we just mentioned this was that this is, you're going to do this all through your scientific career at different sort of scales, where one thing is to get a number, but also you need to qualify how good that number is. That's largely what your job's going to be. Most of the consultancy reports that you might do will have a headline part, which is here's the answer that you asked us to get, and the rest of the report, which will be most of it, will be saying how good or bad that answer is. And then the last bit will be saying, and if you want the answer to be better, pay us some more money. Okay? And it's the same with academic research as well. You have an objective, you state, here is the thing that we found out, and then afterwards it's about how good or bad that is. Now this, and I said this last time, is the atomic detail of that. This is just about making a single measurement. With a single measurement, you also always have to say how reliable that is, because it can't be a true measurement. So I just want you to see that as analogous to everything you're going to do going forward in a larger and larger scale and more complicated things. But even at this most basic level, where your job is just to make a single measurement of something, then you also have to state something about the variability. And that does also relate to the fact that you could do something as simple as this as a project. As we go through this as an example project, which is just based on looking at the difference between different sites. But to just measure the difference between the sites is not science. You need to measure and qualify the variability on each of the measurements. And it's the way that you should think about these things. Once you understand that you can't make a true measurement, it puts you in the right state for doing all sorts of different projects and recognising where research lies.
See, the standard deviation is also just measuring variance, adding up all the differences and dividing by n.
Yeah.
So you've got two ways of doing it.
We're about to just go on to the most fascinating part of this. Okay, I know you're fascinated already, but let's now consider, you come up with this measure of variability that you absolutely understand, but it's not the standard deviation. Okay, let's see why you actually use the standard deviation. All of this is there for you. Like I said to these guys already, that largely your time meeting with me is for me to make you excited enough to do this work, because it's all there on Blackboard anyway, and I've done it very, on Blackboard my little videos are all edited, so there's no ums and ahs and me swearing and stuff. Here you have to listen to that, but it's just, I'm here to answer questions on it and to get you excited about it, but everything's there, so if you think you're missing something, don't worry too much, because it's all recorded as well and it's on Blackboard. Right, now, this part of the argument, what you've arrived at is a measure of variability that you're very happy with. It allows you to compare the variability between different data sets of different sizes, and by knowing the variability, remember, the reason for us wanting to know the variability is to allow us to say how likely it is that our measurement is the true measurement. That's the point of it. Because we can't make a true measurement, so what we need to do is make a measurement and give a number that says how likely it is to be a good measurement. That's the point, that's what we're trying to do. By measuring the variability, it allows us to say that, because if the variability is small, the likelihood of it coinciding with the true measurements is high, okay, which we all agreed, and you can see that from looking at your your frequency distributions, okay. So that's why we need to measure the variability. But the measure that you've got isn't the standard deviation. you didn't know about the standard deviation, well, you'd probably just carry on and think, well, this is as good as we can do. But now we're going to try and figure out why we use the standard deviation. And starting point for that is by it's best here, really. This is where you got to. Job done, like it says. We can compare means, decide which is more trustworthy, because we know how variable they are. The less variable is going to be more likely a more trustworthy one. Although we can't have a true measurement, we can say whether one's more certain than the other. That was our goal. How could we possibly make it any better than that? Well, the thing is, so far attempts to determine whether the sample mean is likely to be close to the true mean have not made use of any assumption about the distribution of the measurement in the whole population. So we've just been assuming there's no pattern for the distribution of the variability. That's the basis that you've been working on in coming up with your measure of variability. Now, why we use the standard deviation is because there is a pattern to the distribution of the variability. And that's, if you've worked through this, you should feel that's like a massive thing to say, right? It's a really, really big deal. That what we're just taking is variability, we've got no idea about it, but actually we're saying that that variability is in some way predictable or modelable. And that's really what this section is about, that random variability can actually be modelled. The best thing for you is to read this, so I'm just going to quickly say what's going on in it. If you think about what you can understand is that to have a large deviation away from the mean, large deviations are going to be rare. Small deviations are going to be more common. And so the distribution of deviations away from the mean, if large ones are going to be rare and small ones are going to be common, then we've got some idea that there's a shape to that distribution. It's going to be shaped like this at least, some sort of triangular shape, because large variations are going to be very rare, so there's going to be very few of them. Small deviations are going to be more common. So you get close to the mean, there's more small deviations away from the mean. So even from first thought, you can recognise that there probably is something predictable about the deviations away from the mean. Now, what you can look at here, which things that you'll have seen before, but I just want to have a proper look at, looking at random processes and the deviations away from the mean that result from them. An example we're giving is the way that particles might move through a porous medium. So this is the way things might move through groundwater. This is going to come back and come back and come back to us, right, in this. You know, I said there's layers and layers on why we're doing this. One, so you thoroughly understand the statistics, but actually these statistics also model environmental processes, and a lot of the environmental processes they model very well are ones to do with transport in the subsurface and where are most of the jobs in environmental science. Because I've banged on and on about this, haven't I? Where are most of the jobs? Yeah, looking at contaminated land, so movement through the subsurface. So as we move through this, the examples that I'm going to start giving when we move to the predicting side, the largest example for you to work through is related to contaminated land and transport of pollutants through that. But it's just using these statistics. At this point, we're using them so you completely understand what this is about, and we're trying to understand why we use the standard deviation. But in doing that, it's got a link to actual physical processes. So the example is looking at physical processes. If you you're best at doing this yourself, right? There's a video there for you to look at, and it just uses a random number generator in Excel. It tells you how to use it, and what we're looking at are a load of particles all lined up together as if they've been dumped there, like a pollution incident, and then they're moved by diffusion. We're going to talk a lot about diffusion, and so is Neil Mitchell, but that effectively means they're moving randomly. If they move randomly, so they can move one unit to the left or one unit to the right, okay, where are they most likely to end up after thousands and thousands of movements? Yeah. Overall, they're not likely to move either way. You know, this is the thing. If you throw a coin that's not biased, if you throw it thousands and thousands of times, the number of heads, number of tails, it's likely to be, the most likely thing is they're going to be the same. Okay? But overall, there's going to be quite a few that aren't quite the same. But ones where you've actually thrown heads 10 times in a row, it's very unlikely. So the chance of me moving to my left, your right, 10 times, this is getting more and more unlikely. Okay? And that means that a particle is very unlikely to move a long way away. So these particles are moving randomly. And then what we're doing is plotting the frequency of these particles at each of these distances. And when we plot that, we've got, you'll see this, there's two different colours. One is the number of particles, and the second colour there is the formula for a Gaussian or a normal distribution. And the two of them actually map on top of each other. Okay. The formula for the Gaussian and normal distribution, it's good that you recognise it. I'm never going to ask you to write it down. Not that it's hugely complicated, maybe some of you know it anyway, but at least recognise it. Okay. And if you go through this, you'll see that. The formula's written down there for you. The distribution of the particles that results is known as the Gaussian or normal distribution. Now, I know you sort of know this. You might even see back in the day, we had to actually spend hours tossing coins and writing these things down. We don't dare ask you to do that now. But this is what you get. And the fact is, you've got a random number generator in any computer that you've got, so you can set this sort of thing up yourself. Okay, once we recognise then that there's you can model the distribution that results from random processes, and you know the equation. There's two variables in the equation for the normal distribution, and these fully determine its shape. So once you talk about a Gaussian or normal distribution, there's an infinite number of Gaussian or normal distributions. Okay, they all have this bell-shaped curve, but you can have flat ones, you can have tall, thin ones. There's an infinite number of them. To specify a particular Gaussian or normal distribution, there's two numbers that control its shape, and that's the mean and the standard deviation. Okay? Now, suddenly, you should be really excited. Right? The standard deviation, which you kind of know is the thing that you use, but that's why you use it. It's almost identical to this measure of variability that you came up with, but it's not quite. You know, the difference is that you're squaring the difference between the mean and each data point. Now, maybe when you actually, if someone did force you to derive the standard deviation before, and you've hated them for it ever since, but if they did that, then they may have said to you that the reason why you square the difference between the mean and each data point is to make sure that the number's positive. You know, we said that if you add all the numbers together, the differences from the mean, the positive and negative differences, by definition, they're going to come to zero, and that's why we disregard the sign. Another option would be to square them. And so people say, you do that so it doesn't sum to zero. But you would have thought, even at the time, well, it'd be better to disregard the sign than to square it, because squaring it does something to the magnitude of the numbers, it changes them. But actually, the reason for it is because by squaring those differences, it means that what you're using is the standard deviation, and the standard deviation is the parameter that controls the shape of the normal distribution, and the normal distribution is the distribution of deviations away from the mean that you would expect if you are looking at random variability. So it's a much, much more powerful statistic because of that, because it's incorporating the fact that you've got knowledge of the distribution. So that's very, very exciting. No? It is very, very exciting. We're going to come back to some of the issues with that, right? Because by using the standard deviation, it means that we are assuming that the deviations away from the mean are wholly controlled by random processes. And it's a massive assumption, and it's one that is overused. Okay, now, I'm telling you that so you can appear to be the smartest people in the room, but at this point, just go with the fact that we're using the standard deviation and know about it properly. The last thing we're going to talk about is what's bad about it. But the talking about what's bad about it is like one level up in terms of.
I'd come up with that squared. I know it obviously gets rid of the sign.
Yeah.
But how is that equal? How does that take into account the normal distribution?
That is the formula for the normal distribution.
Right.
Okay, that's what you get if you do what models random processes. That parameter. Forget that it's called the standard deviation, right? Let's call it. I don't want to say X. I say it's called B.
Yeah.
Then the fact is that B has this formulation of being the difference between the mean in every one of the data points squared divided by the number in the data set. And coincidentally, that's almost the same as a measure of variability that you'd come up with on your own.
Yeah.
Okay, but it's specific to the normal distribution. Okay, so it's that link. So in terms of you making this argument about why standard deviation is the most commonly used measure of variability, that's really the hinging point for it. You can talk about why you need to measure variability, how you might do it, and then there's this link that kind of comes in from the side, really, which is random variability can actually be modelled, and this is the controlling parameter, and the controlling parameter happens to be the standard deviation. Yeah, this is you deriving the standard deviation yourself and then using the standard deviation function in Excel and just seeing that they're the same thing, so you can go through that. One of the things that will come up on this, and people ask me about it, when you type stdv in Excel, it prompts you about whether you want stdvp and stdv. They change it every year, so in 2010. There's various versions of standard deviation. Now the XL93 version is always just standard deviation, but I think they give you 3 or 4 different ones. 2 of them are pretty much the same thing, really. The difference that you need to be aware of is standard deviation P, which is the standard deviation for the population. Now it's unusual that you would use that. Standard deviation for the population means that you've measured all of the points in the data set, the whole population of data points. And immediately that throws a bit of a red flag up to you, because we kind of started off this argument saying that you can't make all the measurements in a population. So for instance, if we were measuring the size of this table, I could measure that an infinite number of times, so you could never use standard deviation P. However, if you were looking at, say, the population of limpets on a foreshore, or the number of garnets in an exposure, you could actually count all of them, and that would be the whole population. If you do measure the whole population, then the statistic's slightly different. For the normal standard deviation, you're dividing by the number in the population minus 1, n minus 1. For standard deviation P, you're dividing by n. Okay. If the data set's large, it makes very little difference, but be aware of it, and it will pop up when you use the function in Excel. And be very aware of it in terms of when we do our multiple choice test at the end, your number needs to be exactly the right number. If you use standard deviation P, it might be out by some part of a decimal point, so make sure you use the right one. In all the things that I'm going to ask you, you'll never be using standard deviation P. Okay, you're just using standard deviation. Now, what makes this even more powerful is because the normal distribution models the distribution of deviations away from the mean, then it actually allows you to effectively make some predictions, really. So you can actually state with some confidence, if the assumption's met, you can state with some confidence, you can give a numerical value to the confidence that you have. Remember, what we're saying is we'd like to be able to say not just this is the measurement, but how confident we are it's the right measurement. And because if we assume there's a Gaussian distribution to the deviations from the mean, so it's always going to be the same shape, then there's certain characteristics of that shape that allow us to say we can give a numerical, we can quantify the confidence. Okay, that's the point. We can quantify how confident we are, not just say we're more confident that this number is more likely to be the true measurement than this other number, but we can put a number on that. We can give a number to say how confident. And that's because the shape of this distribution, proportions of that shape lie within standard numbers of standard deviations of the mean. So again, you'll be aware of these numbers. You might be aware of where they've come from as well, but you may have forgotten. But the point is, with the standard deviation, 68% of the distribution, whichever kind of normal distribution it is, if it is a normal distribution, 68% of the area under the line lies within one standard deviation of the mean. The proportions are the same for all normal distributions. The curve's asymptotic, so the curve never actually hits the x-axis. In other words, the range of measurements are not fixed, and truly random effects could produce infinite deviations in the mean. But an infinite deviation, you'd be pretty bothered about that. I think that can't be right. But fortunately, it's also infinitely rare, so you don't have to worry about it. This exercise, which you should go through, is deriving the d-values. You're aware of these d-values. You know, I think I probably could have beaten it out of almost any of you. If I put a gun to your head, you could have come up with the fact that 68% of the deviation lies within one standard deviation of the mean. And the other one that you would know is that 95% of the area under that curve lies within how many standard deviations of the mean? Close to 2. 1.96, okay, but close to 2. So yes, you've clearly done this before. All right. But what I'd like you to do is just go through this exercise, which is you actually deriving these d-values. That number, one standard deviation, giving you 68% of the distribution. 1 is called a d-value, and for 95%, which is the confidence level we try to work at, 95%, the d-value for 95% is 1.96. Okay, so this little spreadsheet is just for you to derive your own set of d-values. Now, when I was a student, these were printed in tables, and you had to buy a set of tables as part of your. You have to buy a hard hat and a vest, don't you? All right, or a notebook. You guys don't have to buy anything. Well, we used to have to buy a set of statistical tables, and so I'm pretty thrilled with this because this means I'm making my own for free. So I want you to make your own little statistical table. All it is working out the area under this curve. So if you go through that exercise as well. Yeah. And if you weren't already thrilled with this, right? And another thing it means is that if you've got the mean and the standard deviation of the sample, then actually you can make predictions about the population. You can make predictions about things that you haven't even measured. This is really useful for people that are into gambling. Gambling, financial services, which are largely the same thing, life insurance, all these things are based on normal distributions in many ways, and they use them for making predictions. Predictions of how long people are going to live rely on the Gaussian statistics. And in this case, there's a little example for you to do. I want you to work out the likelihood that you actually got a 7-foot tall student. So you measured all these student heights. You didn't actually measure the height of it. You didn't get a 7-foot tall student coming into the building, but you can actually make a prediction of how likely you are to get a 7-foot tall student. Because you can use the mean and the standard deviation from the sample you've got. You can construct your normal curve. And the normal curve predicts everything all the way up to an infinitely tall student. Okay, so I want you to do that exercise as well. You got all these little tests and exercises are not assessed. Okay, the assessment is the 1 hour test at the end. It might have the same questions in it. It might be the questions I'm telling you are in everything, but you should do these exercises because they might be in the test anyway, but you should do them. Okay? But don't beat yourself up over them. Okay. Then we're moving to something that we're going to come back to later on, which is physical environmental processes that are modelled by the normal distribution. And so this is going to come up again and again. It's very important for environmental processes, particularly those in the subsurface, because one, it models diffusion, which is a process by which contaminants can move. That's important not just in the subsurface, that's important in free water. So if you're looking at contamination of lakes and rivers, it's also important if you're looking at atmospheric dispersion as well. We've got an exercise in atmospheric dispersion that also is modelled quite well by Gaussian distributions. And particularly for the subsurface, the way that fluids flow through the subsurface is also modelled by it, because the way they have to flow past grains. So if the fluid comes up to a grain, it chooses to go either left or right to go past the grain. So it's always making these decisions. Well, that sounds terrible. Fluid's not making a decision. There's a choice to go left or right, okay, and it's a random choice. So effectively, you've got the source of random variability in the way that fluids move through as well. So that's why it's so important. And this exercise is to see how you can see the connection between the normal distribution and Fick's law, Fick's first law of diffusion. Again, it's written down here and there, but the first law of diffusion is that the flux is proportional to the concentration gradient. Okay, and Darcy's law, which is exactly the same really. Darcy's law is to do with the movement of fluids. Fick's law is to do with the movement of things in fluids, if you like, the diffusion of materials, both of which are critical to understanding environmental and geological processes, but effectively they're the same. The flux, the diffusive flux, is proportional to the concentration gradient. The Darcian flow of water, the Darcian flux, is proportional to the head gradient. Okay, we're going to talk about both of these when we go through an example, but I'm just mentioning to you now. And so for you to see the connection between those two things, you can run this spreadsheet. And actually, again, there's a video that goes along with this, and I'm talking through it. But it's well worth doing it and thinking about what's going on, because this covers a load of different things. It also covers effectively finite difference modelling, okay, which is something that's very important to environmental science and environmental research and what you might do in consultancy. We have to carry out modelling, and there's a model in this, which is a finite difference model. It's the most basic thing that you can see, but that is what's being implemented in this little spreadsheet. So if you go through this spreadsheet, what we're trying to get out of it is to see the connection between Fick's first law and the normal distribution, and also the process of doing that will actually be a little process of finite difference modelling. We're going to cover finite difference modelling in more detail next week. Actually, we don't have much time, but next week. But you've got plenty of time to look at this. Okay. It's best that you look at it. Basically, you're starting out with something that's normally distributed. If you've got a normal distribution of your contaminant, right, you all know the shape of the normal distribution, right? So imagine this normal distribution in front of us. Whereabouts is the flux, the diffusive flux, going to be greatest in that normal distribution? Right.
On the straight bit, where it's most highest gradient.
Yeah, where the gradient's highest. Okay, so as you pointed out, with the normal distribution, the gradient is increasing and increasing up to Where does it stop increasing, Cameron?
For me, peak.
No, no.
Oh, sorry, it starts decreasing.
You said this at the start. Where does it stop decreasing? Where's the gradient stop decreasing?
The linear bit. It's linear.
It's like one standard deviation.
Yeah. Okay. You said it at the start. The gradient's increasing up to the point where the standard deviation, one standard deviation is away from the mean, and then after that it's decreasing. Obviously on the top the gradient's 0, and then down the other side it starts to increase again when you get down to the standard deviation. So the steepest bit of the gradient is just going to be here because it's increasing. So the steepest part of the gradient is where the flux is going to be highest. The flux is proportional to the concentration gradient. So this spreadsheet is just looking at the difference between two cells. The difference between two cells is the difference in concentration, and you've got a distance, so you've got a gradient. Where the gradient's highest, you get a greatest flux. And so as time moves on, you've got to bring time in. The gradient's going to change over time. It's not the same all the time. The gradient changes over time. So if we start off with a normal distribution like this, over time, what's going to happen to it in terms of its shape? It's like this to start with. What's going to happen to it? Basically, wherever gradient's steep, you're going to have a higher flux, because what it's trying to do is to equalise the gradient. If you equalise the gradient, you go from something that's like this to something that's flatter. So overall, you go from normal distributions like this to ones that flatten themselves out. And the way that it does that is according to Fick's first law. So the point is, if Fick's first law and the normal distribution are really doing the same thing, if you let Fick's first law operate on a normal distribution, let it operate for several time steps, we've broken time down into pieces, if you let it operate for several time steps, the curve that you should get at the end should still be a normal distribution. If it wasn't, then Fick's first law and normal distribution aren't the same thing. Okay, so that's all that's going on in this. And it's worth just having a play around with it, because then you'll see what's going on. And it covers a whole lot of concepts in there. A massive concept is the fact that we're breaking distance down into discrete chunks. So when you talk about a gradient, normally, what's the gradient of a curve? Like, we don't know, unless you do calculus. Computers don't do calculus. Obviously, quite a lot of people don't do calculus either. It's a little bit old-fashioned in that it's all done in the computer now, and the computer does it by breaking distance down into very, very small pieces. And similarly, the same thing with time as well. So this little model, if you like, has broken distance down into pieces, into finite pieces, and it's broken time down into steps as well. We know time runs continuously, but we've broken it down into steps. So very important concepts. We're going to come back to those again and again as well. But this is first, have a go at going through this. We should be able to write our short essay about why standard deviation is the most commonly used measure of variability. I think we've covered everything. Okay, it's the most commonly used one because it's not like the range. It does use all the data points. It's got this very, very useful link to actual physical processes. This is what you want to say. Okay, it's only a short thing, but it's just worth putting the argument together. It's not difficult. All you've got to do is just go through this stuff on Blackboard and just pull out one sentence after the other, but it's worth doing it. Okay, so that's done. Then, using the normal distribution in measuring and predicting, this is what can be at the heart of lots and lots of projects. So simple projects that are just comparing one thing with another. We can do this now. However, there's a couple of, I think there's 3 more things that we need to say before we can make our comparison. If you think about the objects, my objective over, I don't know, this chunk of work was to set you up for doing projects where you can say the concentration at this site is different to the one at that site. And that's what you set out to prove. Your hypothesis there is a difference, or this microbe was actually able to convert more tetrachloroethene into something that was harmless than this microbe was. Right? There's loads and loads of projects that are like that. Follow the process of setting the project up. Ultimately, the way that you're setting your experiment up, the way you can analyse the data, is just relying on the fact that you can show definitively that there is a difference between treatment A and treatment B, site A or site B. Right? If you can do that, there's hundreds of projects that people have done over the years that just rely on that, and they are clearly bits of science if you do that. Okay, but we're still not quite there. It appears you're now able to make measurement useful as you related the sample mean to the population by a probability of their coincidence. However, these 2 other things you need to consider: variation of means versus variation of measurements, and the sample size. I don't know. I'm not. You should go through this. I'm going to quickly say what's going on here. If I deal with the second one first, because it's a little bit easier. In our consideration so far, in working out a standard deviation, we haven't considered how many are actually in the sample. Okay, yeah, we've standardised it by dividing the number in the sample, but we haven't considered how many are in the sample. The point about that would be, if you'd done an experiment that you repeated 5 times, and someone had done an experiment that they repeated 50 times, and you both got an answer, you know that the answer from the 50 replicates would be, you'd trust that one more. But there's no accounting for that if we just look at the standard deviation. It doesn't feature in there. So we know there's something missing. We do need to account for the population size. And the way that we do that is that we don't use the d-value. So we've said that for 95% confidence, the d-value should be 1.96. But actually, we don't want to use the d-value. We need to use something else. If the sample size is small, then we need to use the t-value rather than the d-value. You don't have to derive them. You can get it out of Excel. I just want you to understand what's going on. And the best way to do this is for me to use my hands. I really need to use both of them, but one's occupied. But if you imagine you've got 2 points, one here and one here, what we're trying to do is to say that these 2 points, are they different or not? One here and one here. First of all, those points are the means of several samples, okay, and we've got a standard deviation for them. We know that if we want to be 95% confident those points are different, we need to draw an error bar on them and see whether the error bars overlap. If the error bars don't overlap, then we can be 95% confident they're different. So imagine the error bars on these points. If we use the standard deviation and the d-value, so we multiply the d-value by 1.96, sorry, we multiply the standard deviation by the d-value, so multiply the standard deviation by 1.96, we get an error bar like that on one of the points, and on the other point, we do the same thing, all right? Multiply by 1.96, and actually, yeah, they're overlapping. So we can't be 95% confident they're different, but we haven't actually accounted for the size of each of those samples, and we shouldn't be using the d-value, we should be using a t-value. Now, the d-value, really, how big should the sample size be to legitimately use the d-value? You guys are excused, but you guys, last week, no, whenever I ask you a question, it's always the same answer. Do you remember what the answer was? No. Infinite, right? The answer's always infinite. So really, to use the d-value, the population size needs to be infinite. That's the way it's calculated. But you will have heard again, it's one of the things that you will have heard. How big does a sample need to be to count as a large sample? You've heard this. What's the number?
Greater than 30.
Yeah. Generally, people say greater than 30. You would always, that which you've kind of thought, what's that about? Right? What that is about is the coincidence of the D and T distributions. So once the sample size gets to about 30, the T values and the D values are almost the same. So you can use the D value rather than the T value. Now, because you've got access to a computer and everything, you should check that out really. Right? Really, the thing about the sample size being 30, I think, comes from back in the day when it was a bit of a pain to look at the T values. But the T value and the D value, when you've got a sample size of 30, they aren't the same. There's still a difference between them. And it's no trouble for you to use a T value. It says in there, and it's on one of the videos, the function that you need to use is the T inverse function in Excel, TINV. Use the T inverse function, that returns the T value for you. And the T value, the parameters to decide the T value include the sample size, whereas for the D value it doesn't. The D value assumes it's an infinite sample size. The T value includes the sample size. So if we do that, the typical thing is you've done things in triplicate. So you've done your triplicate sample. Our first attempt at this, we multiplied our standard deviation by 1.96 because we were interested in 95% confidence. However, because it's a triplicate rather than infinite sample size, we should use the T value. The T value for three samples means you've got degrees of freedom of n minus 1. So degrees of freedom of 2, and we want a confidence of 95%, which is 0.05. That's what you'd enter into Excel to get your value for the T value. The value you'd get would be 4.303. That's maybe a number that's even worth remembering, because you're always doing things in triplicate. And when you do it in triplicate, the T value is 4.303, which is more than twice 1.96. So what's going to happen to our error bars? Our error bars are going to get twice as big. So before, we had these two points that were slightly overlapping with each other. Now the error bars have doubled in size. They're completely overlapping. We can't be 95% confident they're different at all. So our error bars have appeared, they've grown. Now a little bit of good news is that we can make them shrink a bit more, which is the second point. We're actually interested in the variation of the mean rather than the variation of the whole of the sample. We're looking at variations of the mean. And there's a little exercise, put it right somewhere, yeah, here. It even says 5 bonus. It doesn't really mean anything. I've given up on that. That's what we used to try and mark these things. I'm not sure. I think very occasionally some people will do this, but what you can do is if you take that set of 500 student heights, if you break it up into 50 sets of 10, and you work out the means of the 50 sets of 10, and work out the standard deviation of that set of means rather than the whole of the data set, you'll see that the standard deviation is less. So the standard deviations of the means are less, the variability is less, and what we're actually looking at in this case is a mean, and we're trying to say we're 95% confident that these means are different, not that we're 95% confident that any of the samples within those means are different. Okay, the net result of all this is that whilst the T value is making our error bar bigger, we also can adjust for the fact we're looking at means, and the adjustment for that means that we can divide the confidence limit by the square root of the number in the sample. The actual mathematics of that is actually quite involved. We don't need to go there, but just sort of understand what's gone on. And the best way of thinking about it is imagining our error bar. First of all, our error bar is drawn with a D value, and it's this big. We draw it with a T value, it gets much bigger. But then, because we're concerned with the variability, the variation on the means, we can actually reduce it. And the reduction is by dividing by the square root of the number in the sample. So the confidence limit, which is ultimately what you want to plot, the confidence limit is the standard deviation multiplied by the t-value divided by the square root of the number in the sample. That's the confidence limit. And that's the thing that you're mostly going to be plotting, okay, if you're trying to say one thing's different to another. Okay, and this is sort of the most basic statistic that you're going to use, but I said to you at the start about this, lots of people still do it wrong. The reason why you want to do that is because those error bars then have a very specific meaning. If they do overlap, then you can say that you can't be 95% confident that these numbers are different. If they don't overlap, then you can say you are 95% confident, or at least 95% confident those numbers are different. Any other error bar you draw on there, you can't say that. Okay, if you just draw, a lot of people, well, not a lot of people, sometimes people draw the error bars just the standard deviation, but then there's not something you can actually say about that. Okay, you'll see error bars on things, the error bar is the standard deviation, or even the relative standard deviation, but it doesn't allow you to say, I've got 95% confidence that these numbers are different. The only way that you can do that is by drawing a confidence limit. And often, if you think about it, like putting an error bar on, it is what we should be doing. We've got to give some idea of the variability, but you can't put into words what that error means. You kind of, I suppose in some ways, the information's there. If you just plot the standard deviation, but it's a bit like, you know, I've been saying to you, your job in writing your thesis is not to just film yourself for 3 months and throw the video onto the table and say, there you go, pick the bones out of that. It's true, it's all in there, but you're not doing your job. And similarly, like if you plot the standard deviation, the fact is the information's there. If you give the number in the sample, so someone can go away and work it out, but that really isn't the point. You want to have error bars that mean something. Okay, then there's a little task for you calculating some standard errors of some polluted sites. There's a full-on exercise on doing this which you can choose to do. It's a writing exercise as well, which comes up a bit later, but there's a little calculation there for you. It's worth doing the calculation things because, well, anyway, it's just worth doing them. Why are many measurements predictions? We talked about this last week. I set the thing up that we're talking about measuring and predicting, but actually the things overlap. And after going through all this, you should really be able to answer the question, why are many measurements themselves actually predictions? You should have a feeling about why that's the case. The fact is you can't just make a measurement. A measurement on its own is fairly useless. So there's something else that goes along with it, and the thing that goes along with it, this measure of variability, in some ways a prediction, isn't it? Because we're using the normal distribution to make some sort of prediction. So that's really what you need to be writing there. But think about that. You should see that actually measurements themselves, once you say we can't make a true measurement, then it's likely there's some kind of prediction in there. The prediction is really to do with the variability. Then this little summary essay, it's less than a page. It's just pull those points out and put them in the right order. Yeah, and this is this bit that I said to you. I kind of want to excuse myself now in that I spent ages banging on about the normal distribution, how important it is, and that's what you should, you know, the fact is, like, lots of people, lots of projects don't use it at all, don't use it properly. So the most important thing for you to do your first job is to get a first class mark for your thesis, and using this properly is it's going to help you most in doing that. This bit is about education, okay, and I would be remiss if I didn't tell you that you should consider that quite often the normal distribution is used incorrectly. It's not appropriate to a lot of things. There's huge problems with the way it's been used. Stuff in the financial sector, that's to do with other distributions as well, but many other things. So there's a book called The Cult of Statistical Significance, which is just taking the thing apart, about largely to do with medical trials. Okay, there are huge problems with using normal distribution. Now, as I said to you before, well, I see you guys are here now as well. Do you read books? We have a load of people in here that actually have the nuts to even admit to not reading books. But anyway, lots of people don't read books. So if you're not going to read the book, then I've even given you another little podcast here, which you can just listen to. But it's worth listening to that. How standard error costs us jobs, justice and lives. I really recommend that you read that. Sorry, listen to that. It's only 20 minutes or so. Have a listen to it, and then I feel like I've done my job of educating you. I have this job of training you to get the best possible mark, and all this stuff on normal distribution, really, really important. Do that, but do listen to this. Otherwise, I feel like I've misled you. Right. And the fact is, how many of you listen to the weekly statistical podcast on Radio 4 anyway? Well, honestly, you should do. Right? This is your first go. Have a listen to it. Like, it's very, very. It's all about topical things. Like, is anyone interested in football even? I'm failing all. You are. I know you are. The archive's full of them. There's one about how teams get their FIFA grading, and all statistical nonsense and rubbish in that. Anything that you're vaguely interested in. Loads of political things. It's good to start listening to the statistical podcast. Who's going to listen to the statistical podcast? You're not even prepared to lie to me. So, you won't regret. You know, there's very few things that I can say, tell people to do, and I know it won't be a mistake. There's a few books I could recommend, but I have no problem recommending. But that, just listen to it. You will listen to more and more of them. I'm jealous of you. I've listened to them all already, but they're all just there for you guys. So, but do listen to that one. All right. Okay, we've spent a lot of time working out the best way of measuring variability, and before that we'd recognised that in order to measure variability we need to make multiple measurements. So we've generated loads and loads of extra work for ourselves. Like, you're not going to do your experiment once, you're going to do it 3 times, okay, at least. So 3 times as much work. So you do all that, and then you have to go through the process of deciding whether it's normally distributed. All this, you do the statistics. I've generated loads and loads of work for you. Now, the next step is you analysing and using that data. So if the next thing you need to do is to take the number that you've got, say it's the concentration that you've measured in a water, and then we actually want to know how much contaminant's moving, so we need to multiply it by the amount of water that's moving. Measuring the amount of water that's moving, something we're going to do on a field trip, it's a pain in the arse to do it, and you're going to have to do that 3 times as well, so we've got an error on that. So there's 3 times as much work at least that's gone on in making our measurements. So when you take the 2 measurements and you put them together, the last thing that you want to do is forget about the errors when you do that. You multiply the 2 numbers together, you need to know what to do with the errors. It's critical. Like, you spent all this time and effort working out errors, you need to make sure that you keep them in the calculation as you move the data through. And so this is propagating errors. What do you do with errors when you add numbers together, when you multiply numbers together? Again, this will have been mentioned to you before, probably. it's written down here for you, and there's an example for you to go through. It's really important that you do this, so you know what to do when you actually deal with errors. Again, you'll look like, the more that you can go on about errors is the way to look like the smartest person in the room. It's just such an easy way to pick holes in people's work. And it means also that when your work's being marked, like, no one's really got the time. No one wants to be marking it. And so they're looking for the easy ways of saying, what's wrong with this? And you can almost, without reading it, say, oh, they haven't done enough statistics on it. They've not considered the errors in each of the measurements. So don't fall into that trap and be the other side of that fence. Be the person that's always saying, you haven't given me an error. If someone gives you a number ever, you can look like such a smart ass, but not wrong by saying, oh, what's the error on that? Okay, and propagating the errors particularly as well. Make sure you propagated the errors through. It looks complicated. Well, I don't know. You may think it looks complicated, but if you analyse what's written down there, it's not that complicated. So rather than just carrying out the formula like a robot, I'd think about it a little bit. Actually, to derive these formulas for how you propagate errors, you need to do partial differential equations to actually get to these. So we're not going to do that. But you start to recognise them. So for adding errors together, you add the two numbers together, but to add the errors together, you square each of the errors, add them together, and then take the square root. That should at least make you feel a bit reminiscent of standard deviations, or, you know. There's a little feeling for that. You know, you're squaring them. You are adding them together, but you square them first and you square root them afterwards. So you can kind of see how it's gone. We square them, they're big, add them together, square root them, they get smaller, right? That's what's going on. And you're doing something similar with multiplication. With multiplication, it deals with this fractional error, which you work out, but you have to scale the fractional error by multiplying by the resultant quantity. The resultant quantity is the two numbers added together, and you can understand that if you're multiplying, there's a scaling factor. You work out the actual error, and then you scale it according to the size of the number that you're dealing with. That's what's going on there. Okay, but again, it's all written down, and if you work through that, actually, what you can work through is there's a little example here for you. So best thing to do is to work through the example. The example is of a discharge consent. So typically, polluters are granted a consent to discharge a certain amount, and that amount will have an error on it. And you've got some details here of someone who's discharging to a watercourse. There's a variability in the concentration of discharging. There's a variability in the amount of water that's flowing through, and so you can work out how much he's actually discharging in a 24-hour period and see whether that falls in line with his consent. Okay, and all you need to do is to use propagation of errors by multiplication and by addition in order to do that. Okay, so the best thing to do is just to work through it. Again, if you get stuck or anything, it's not a bad thing. You're not going to lose any marks, and just ask about it next week. But do have a go at it. That's the main thing. If you don't have a go at it, it's like we haven't got anything to talk about even. But have a go at doing it. It's not difficult. It's best to set up a little spreadsheet for doing it. You know, the first thing to do is work the numbers out, multiply the numbers together, get the actual numbers, and then consider what you're doing with the errors. Okay. And ultimately, the question that's asked at the end is the discharger within his consent? We just need an answer to that. Okay. Right. Yeah, you saw, this is my version of Blackboard where you can see everything, and there's a complete, the spreadsheets that you've been working through, I've got the answer sheets, and I'll put those up at some point. I mean, it's pointless me putting them up now, but I will put them up, so before you have your test, so you can make sure you've got everything right. Yeah, this is just, again, saying the same thing. warning, need to control systematic variability and the lack of control in the natural environment. But again, this is really useful. If you start with this fundamental thing, if you can't make a measurement, so what we need to do is to make a measurement and also have some measure of variability, some measure of how good the measurement is. If you have that running through your mind all the time, then it helps you to design an experiment, and it certainly helps you in explaining why you've designed it and how you've designed it. The magic of these parametric statistics, those ones that make reference to normal distribution, i.e. standard deviation, it works if errors are random or normally distributed. The only error to be present when using parametric statistics is a causal error that can't be controlled, error that should be normally distributed. So the assumption is that that's the only error that's left. So when you design an experiment, designing an experiment is, so the only variability that should be left in it is the acausal variability. Okay, and there's a good way of sort of getting your head around this really is there's an example that I've given you. Don't have to do it, but there's an example little project that you can work through, and it sets up a sampling and analysis program, and it's written in terms of trying to remove the variability. You're generally interested in how something varies with something else. So in the example, you're interested in how metal concentration changes with distance. Okay, that's what you're trying to find out. So in order to just have those things as the variables, you need to control the other variables, all the ones that you can control. So if there are any other reasons why the metal concentration might vary, in this case we're looking at metal concentrations in a biomonitor, which is seaweed. So it might be that the metal concentration will vary in the seaweed, not just because of distance, but because of the type of seaweed, or the amount of the time the seaweed spends under the water. Experimental design means removing those things as variables. So the easiest one straight away, to remove the variable of it being different in different species, is that you'll use the same species. Okay? I know it's obvious, but it's just the thinking pattern that goes into that. What you're trying to do is to isolate the variables that you're interested in, and you keep isolating variables until the only variable that's left is the variable that you can't control. And the assumption is that the uncontrollable variability is distributed normally. And that's a test that you can make, like by thinking about it. Is this variability that I'm not controlling, is it likely to be distributed normally? So in the case of this seaweed exercise, which is looking at the concentration in seaweed as you move further away from what might be a source of the contamination, well, we need to control the species of seaweed that we use. That's fairly obvious, we'll just use one. The seaweed can spend different amounts of time underwater. If it's not underwater, it's not going to be exposed to the metal. So we need to make sure that we take seaweed that is underwater for the same amount of time. And the way that you do that is by choosing seaweed that's at the same position on the shore all the time. The seaweed that's older will have been exposed for longer. So we need to control the age of the seaweed. The way that we can control, for seaweed grows from the end, from its tips. So if you sample by measuring 5 centimetres back from the tip, you've always got seaweed of the same age, or the same youngness, if you like. So that's been done. But, you should all care about seaweed in metals. It's actually a standard way of assessing metal contamination in coastal environments. Okay, so you should care, but some of you may not. But the thought process in designing the experiment is always controlling the variables that you can control, ultimately to leave the variable that's uncontrollable, and that can be modelled by using the normal distribution. So if we controlled those variables, then what we're left with are things like the micro topography around the seaweed, like if it's behind a boulder or something like that. Now you may try and control that, or you may decide that actually that's going to just be uncontrollable variation. Also the fine sort of genetics as well. We say we're going to use the same species, But even within species, like you and me, same species, but we're different. Okay. Similarly with seaweed, might be the same species, but there can be some differences. Might be some slight differences. We're going to throw that into the uncontrollable variation pot. Now, actually, if we turned out to get some anomalous, unusual results, we might have to go back and review what we consider to be a causal variation. And again, that's the process of scientific study working. But that process is control the variability that you're trying to control. What you're left with is the uncontrollable variability. And what do we do with uncontrollable variability? Well, one where we model it by the normal distribution, but actually, more fundamentally than that, the uncontrollable variability, we try and quantify it. So you control the variability you can, the uncontrollable variability we quantify. What's our first requirement in actually trying to quantify that variability?
Number of samples.
We need to do multiple measurements, okay, and that's where you end up with, like with the seaweed thing, the uncontrollable variability, we quantify it, and in order to do that, we need to make multiple measurements. And by experiment, it's a standard method using seaweed as a survey tool. It's recognised you need to take at least 10 replicates. So when you take the sample, you need 10 replicates of it in order to quantify the variability. Okay, and that means you can pop your error bar on it. Okay. This is written down as an exercise. You can work through it. It's a little thing to write up. It's an example.
Yeah.
That's it. You can listen to the video, whatever. You can write the thing up, but it's there for you to go through it. Just aware, you do have a load of time, so you can spend your time looking at that. This is also important, and it covers some terms that you really should be using and things that well, I'm sure you are aware of, but you need to be aware of. I'm just going to let you just go through. Make sure you do go through this. Like one of the things, my little flag to you in terms of what might be on your test. Make sure that you know the difference between accuracy and precision and resolution. Okay. You should get that from this. If you don't, then ask me about it and look it up. But accuracy, precision, and resolution, and really, really important that you understand what those are about. And then you can start using those terms accurately. It's going to come up with some of the things I think that we actually do on the field trip as well. All the analysis needs to be couched in terms of accuracy, precision, resolution. And if you think about it like this, if you're writing your thesis, you have your method section. A huge part of the method section, the method section is there so people can repeat your work. So there needs to be enough information in order that they can repeat your work. So that's one way of judging what needs to be in there. The other side of what needs to be in there is something to give the reader confidence in your data. It's also, you don't have the right to waste anybody's time or take their attention. Okay, and you need to say as soon as possible about the quality of your data, because then they can decide whether it's worth reading on or not. So the things that also need to go into your method is some idea of the accuracy, precision, and resolution of the methods that you're talking about. That's what people will be looking for. And again, it's the easiest thing to try and take some marks off you. So consider it in writing your method. Check with yourself, have I covered the accuracy, precision, and resolution of the data? Because if you don't know that before you move into the results section, then you don't know how much weight to place on the results. It's critical that someone knows that. And so just remember, you need to know that. It's very important. We can talk about it next time if there's any gaps. The standard way of thinking about it, which isn't actually on here, so this would be worth making a note, those of you who don't know this already, but if you imagine a dartboard, okay, and if you throw an arrow at the dartboard, if it hits the bullseye, then it's accurate. You have to recognise the bullseye, we'll talk about this again, but the bullseye is really the standard that you're comparing to. If it hits the bullseye, it's accurate. If the darts all group together, whether they're on the bullseye or not, then it's precise. Okay, so it's repeatable and precise. And resolution is to do with how narrow your dart tip is. So typically a dart is something that will stick into you and is quite sharp, but if you throw a dart that's as wide as the dartboard or as wide as the bullseye, then the resolution's quite low. Okay, so it may be accurate because it's hit the dartboard and covered the whole dartboard, but the resolution's quite low. So accuracy and precision resolution are shown up quite well in the sort of dartboard analogy. The missing thing for that, though, is to understand about accuracy. Accuracy can only be judged against the standard. Okay, and we'll talk about the importance of standards when we talk about stuff from the field trip. All right, but we should have a 10-minute break, and then I'm just going to go through the other section. I don't need to spend long on it because really it's there for you to look at, but I just want to make you excited enough to look at it, however successful that is. Okay, so 10 minutes.